The exhaust system of a gas turbine engine is an often underrated part of the propulsion unit, yet its design exerts a considerable influence on the performance of the engine. The gases which discharge from the turbine must exit in the correct direction and at the optimum velocity to provide the thrust of the turbojet engine. While in the turboprop engine, where the thrust is provided by the propeller, the turbine gas temperature and back pressure at the turbine are, to a large extent, dictated by the design of the outlet nozzle. The temperature of the gases entering the exhaust system can be between 550 and 850 degrees Celsius. This temperature can rise to as high as 1,500 degrees Celsius if an afterburner, sometimes called a reheat system, is used. The fuselage of the aircraft, if it has the exhaust system running through it, as happens with most jet fighter aircraft, must be protected from these temperatures. This is done by both allowing a clearance between the jet pipe and the aircraft skin, through which air is allowed to circulate, and insulating the jet pipe with some form of fibrous material sandwiched between thin layers of stainless steel. The velocity of the gas as it leaves the turbine can be between 750 and 1,250 feet per second. This is somewhere around 0.5 Mach. If this gas has to negotiate a long jet pipe before being ejected into the atmosphere to provide thrust, a great deal of turbulence will be caused within the pipe. This will lower the efficiency of the engine and reduce its thrust. This diagram shows the basic layout for the jet pipe of an aircraft without afterburners. Although the shape of the jet pipe outer casing appears to be convergent at the point where the gas leaves the turbine, the shape of the volume within the casing is in fact divergent. The divergence is made possible by the insertion of the exhaust cone, a conical-shaped device positioned close up to the rear turbine disc rear face. As well as helping to reduce the velocity of the gases leaving the turbine before they pass down the length of the jet pipe, so minimizing turbulence, the exhaust cone also prevents the hot gases flowing across the rear disc face of the turbine, further reducing disturbance and preventing overheating of the disc. The rear turbine bearing is also supported inside the exhaust cone via turbine rear support struts, which are streamlined by fairings. The fairings also straighten out any residual whirl which may exist in the gas stream as it exits the turbine. This residual whirl would cause additional losses through generating turbulence if it was allowed to pass into the jet pipe. The exhaust gases travel down the jet pipe and finally exit to atmosphere via the convergent propelling nozzle. The convergent propelling nozzle increases the gas velocity to speeds of Mach 1, the speed of sound in relation to the temperature of the gases, in a turbojet engine at virtually all throttle openings above idle. At this velocity, sonic speed, the nozzle is said to be choked. The area around operating gas turbine engines is inherently dangerous to personnel and equipment. This diagram indicates the primary danger zones around the intake and exhaust of an engine similar to the type fitted to the Cessna Citation. The more powerful the engine, the further these zones will extend from the engine. Notice that the gas velocity exiting the engine is extremely high, as is its temperature, although the levels of both drop quite dramatically with increasing distance from the exhaust nozzle. Foreign object ingestion is an ever-present danger to gas turbine engines. This short video graphically illustrates the perils facing both personnel and equipment when they are in close proximity to engine intakes. The area behind an operating gas turbine engine is just as dangerous as the intake area. This short video was staged to show what can happen if the engine exhaust danger area is entered without recognition of the perils involved. In the convergent exhaust duct, the shape of the duct accelerates the gas. In a turbojet, the gas flows at subsonic speed at low thrust levels only. At almost all levels above idle power, the exhaust velocity reaches the speed of sound in relation to the exhaust gas temperature. At this point, the nozzle is choked, which means that no further increase in velocity can be obtained unless the gas temperature is increased. When the gas enters the convergent section of the convergent-divergent nozzle, its velocity increases with a corresponding fall in static pressure. The gas velocity at this point now reaches Mach 1. As the gas flows into the divergent section, it progressively accelerates towards the open exit. The reaction to this increase in momentum is a pressure force acting on the inside wall of the nozzle. A component of this force, which acts parallel to the longitudinal axis of the nozzle, produces the further increase in thrust. Having two gas streams to pass to atmosphere makes the exhaust system of the bypass engine a slightly more complex affair to the essentially simple systems we've examined so far. The low-ratio bypass engine exhaust shown here combines the bypass air and the hot exhaust gases in a mixer unit. The mixer unit ensures thorough mixing of the two streams before they're ejected into the atmosphere. This picture shows two methods which are used to exhaust the cold bypass air and the hot exhaust gases. The top illustration shows the standard method whereby the hot and cold nozzles are coaxial and the two streams mix externally. Greater efficiency can, however, be obtained by fitting an integrated exhaust nozzle, which is depicted in the lower illustration. Within this type of unit, the two gas flows are partially mixed together before their ejection into the atmosphere. This diagram shows relative sound levels from various sources, some of the highest among them being aircraft engines. Although an aircraft's overall noise signature is a combination of sounds which stem from many sources, the principal agent is the engine. Airport regulations and aircraft noise certifications governing the maximum noise level which aircraft are allowed to produce have forced rigorous research into ways of reducing that noise. The most significant source of noise from the engine originates from the compressor, the fan in the high-ratio bypass engine, the turbine, and the exhaust. Although the noises which spring from these various sources all obey slightly different laws and mechanisms of generation, their levels all increase with greater relative airflow velocity. The level of noise from the exhaust is more affected by a reduction in its velocity than the noise levels of either the compressor or the turbine are. It's logical, therefore, to expect that a reduction in exhaust jet velocity would have a stronger influence in reducing noise levels than an equivalent reduction in either compressor or turbine speeds. The relative speed difference between the exhaust jet and the atmosphere into which it is thrusting causes a shearing action. The shearing action, in turn, creates a violent and extremely turbulent mixing pattern. Here, where the turbulence zone is narrow, is where the high-frequency noise is being generated in the mixing pattern. And here, where the turbulence zone has widened, the low-frequency noise is generated. The noise of the exhaust of a pure turbojet is of such a high level that the noise of the compressor and the turbine is insignificant, except at very low thrust conditions. The exhaust noise of a bypass engine drops because of the reduction in the velocity of that exhaust. But because they are handling a much greater power, The turbines and the low-pressure compressor of such an engine generate a higher noise output. In the case of a high-ratio bypass engine, say an engine with a 5:1 bypass ratio, the noise from the jet exhaust has been reduced to such a degree that the noise from the low-pressure compressor, the fan, and the turbine are now predominant. Having reduced the noise levels emanating from the main source, the exhaust, engine manufacturers then concentrated on lowering the levels of noise from the rest of the engine, specifically the fan and the turbine. The use of the type of noise-absorbing material which is shown here in the engine intake and the bypass duct is extremely efficient in reducing noise in those regions. Further down the engine, in the hotter zones, slightly different materials are used to great advantage in the same quest for noise reduction. The disadvantage of the use of these materials is that they add a small percentage in weight, and that their skin friction is slightly higher than the material that would otherwise be used. Together, these factors cause a slight increase in specific fuel consumption. Whereas the modern gas turbine engines could take advantage of the new methods of sound-absorbing materials, aircraft fitted with older, pure turbojets had to find some other system of reducing their noise output. Aircraft can still be seen with corrugated internal mixers and lobe-type nozzles fitted to the rear of their power units. The latter cause the gases to flow in separate exhaust jets that rapidly mix with slower-moving air which is trapped by the lobes. The corrugated internal mixer was most efficient at reducing exhaust noise, but unfortunately it also induced performance penalties that limited its popularity with aircraft operators. This concludes the lesson on the exhaust system.